All right, lads and ladies, welcome back to Calc 2. You may notice that we are in a slightly different place than normal. This is the back room at my house where other sorts of people do stuff like that. The aim here is to get you guys kind of a little bit less of the baby noise and the puppy noise and have a slightly more focused environment. Hopefully it worked, and hopefully you enjoy the slightly less distracting situation. We have been talking about improper integrals, and we're moving forwards in this new part of the course where the focus is on convergence, right? Looking at objects that may converge or may diverge. Improper integrals of type 1 or type 2 are sort of the first things that we meet like that, and you've now had some time to play with those. Today, we are going to begin talking about a new family of things like that called sequences. And I just want to take a quick look at your homework situation here to make sure we are where I thought we were. I didn't split this into two, right? You have 1 7.8 homework with all of this type 1 and type 2 integrals, yeah? Yeah. Yes, indeed. Okay. So we are now comfortable with what it means for an improper integral to converge or diverge. That's where I expect you guys to be, and capable of computing improper integrals. So we're done with improper integrals. That's it. The next set of things that we will talk about converging or diverging are sequences. And then out of sequences, we will build these things called series. So everything kind of stacks. And this is a little bit tricky. We're going to be using a lot the stuff that you learned in Calc 1 about limits at infinity. And hopefully you kind of followed my lead last time and decided to brush up on that stuff if it's something that you were rusty with. Let's get started. This is MAC2312.004, which means we're talking about Calc 2. And the date today is 10/4/21, the 4th of October. Can you believe it's already October? Today, we're talking about sequences, which is section 11.1. So it's a big jump in the book. We're going to come back to like chapters 8 and 10 a little later in the course, but it makes sense to put all the convergence stuff together. They all work well with one another. Again, the reference material that you may want to look at, I did add some stuff to the modules for you guys last time. That's pretty cool. There's now stuff in here about L'Hopital's rule. See down at the bottom, I added a bunch of things for L'Hopital's rule. So if you're sketchy on L'Hopital's rule, there's lots and lots of stuff for you to look at here now. I don't think I have any. Yeah, all the other stuff is from later in the learning. So that L'Hopital's rule stuff is going to be important for sequences, but there's other techniques relating to limits at infinity that are important as well, right? Everything from section 2.6 in the textbook. All right, there's only one place to get started with this, and it's a definition. There's kind of two ways to define a sequence. One is quite formal, the other is quite informal, but more intuitive. So informally, a sequence is a list of numbers. That's it. So there's a first thing, there's a second thing, there's a third thing, and that list, that infinite list, is called the sequence. Formally, a sequence is a function from the natural numbers for us to the real numbers. All right, a function from whose domain either the set 0, 1, 2, 3, and so on, or just 1, 2, 3, and so on. People argue about which one of those sets is the correct natural numbers, whether you include 0 or not. It doesn't fucking matter. But more intuitively, a sequence is a list of numbers. I think the first little hurdle we need to clear here in order to understand this stuff is the notation. So normally, when you write down a function, you write like f of x, right? F of x equals, and then some formula for the output in terms of the input. Here, because the independent variable is always an integer, we use the symbol n for the independent variable. And also, instead of writing like f of n, we write a sub n for the output. A little bit more notation. Maybe let me give you some examples before I show you like the rest of the notation, because it'll make more sense with a few examples under your belt. All right, so some examples. Hold on. 0, 2, 4, 6, 8, and so on. Here's a list of numbers. Right? It's a list of numbers, so that's a sequence. It goes on and on and on forever. That's what's implied by the ... dots. And it goes on and on and on forever in that same pattern. So the next number in this list is not 9, it's 10, right? And then not 11, but 12. This is the sequence of what? If you had to describe this list of numbers to somebody, what would you call it? Now, everybody here knows this. Don't think too hard.
Even numbers.
Mm-hmm. And if I wanted to, I could try to find an algebraic representation of this sequence. I could call this guy A0 and call this guy A1, A2, A3, A4, and so on. And then try to find a formula for AN in general. There was a suggestion in the chat, which, well, a good suggestion is not quite right. So when n is 0, we get out 0. When n is 1, we get out 2. When n is 2, we get out 4. When n is 3, we get out 6, and so on. So a formula for the nth term, like I would call this the 0th term, I would call this the first term, I would call this the second term, and so on, is an equals 2 times n. All right, and if you plug in n equals 0, 1, 2, 3, 4, you will get out these numbers in this order. Bueno. Other example. 1, 3, 9, 27, 81. This is also a sequence. It's a list of numbers, so it's automatically a sequence. If you had to describe this sequence in words to a human being, what would you say? How would you call it? This one might be a little less obvious.
A sequence of the previous number multiplied by 3.
That's true. Yeah, to go from one to the next, we multiply by 3. And since we started with 1, that means these are all going to be powers of 3. And if I again want to call this guy A0, call this guy A1, call this guy A2, call this guy A3, call this guy A4, then I could write a formula for the nth term. An here would be just 3 to the n. Right. 3 to the 0, that would be A0, that's 1. 3 to the 1, that would be A1, that's 3. 3 to the 2 would be A2, that's 9. 3 to the 3 would be A3, that's 27. 3 to the 4 would be A4, is 81. All right, I think we're in a good place now to discuss the rest of the notation. Some more notation. You'll notice in both of these examples, I started n at 0, right? In both of these examples, I'm using this for my domain. I could have, in either of those instances, used this for my domain, but it would have required shifting things a little bit algebraically. In general, when I write down a sequence, like if I just tell you an equals 3 to the n, unless I tell you where n starts, that doesn't completely determine the sequence, right? If I just tell you an equals 3 to the n, and I don't tell you that n starts at 0, you might think that that sequence is just 3, 9, 27, 81, blah, blah, blah. You might miss the 1. So to refer to the whole list as a single entity, we write curly braces an. Other kind of slightly, like when you get into analysis, sometimes people like to use parentheses instead. It doesn't matter, but your textbook uses this. So if you see an or a formula like 3 to the n inside curly braces like that, they mean the sequence of terms built out of that formula. And down here, up here, you'll see the starting value for n. The infinity up there sometimes is ignored because it's always infinity, but this will be the starting value for n. Okay. So what I'd like to do now is I'm going to give you a sequence in this notation, and we're going to write out the first few terms. Any questions so far? Just curious, go ahead and take a second to find your reactions in Zoom. I am curious, how many of your pre-calculus classes actually got to talk about sequences? Go ahead and give me a thumbs up or any sort of react. I don't care. Give me some sort of reaction in Zoom if your pre-calculus class did talk about sequences.
Yeah.
Okay, most of us. That's reassuring. Very, very good. All right. So we're not going to beat the notation to death then. We'll just do one of these really quick. And then we're going to start talking about what it means for a sequence to converge. Look at some graphs. So let's write the first 5 terms of the sequence how's about this? So the terms are, where an is n over n squared plus 1, and n starts at 1, goes on forever. Okay. Well, we know that an is n over n squared plus 1, and n starts at 1. Right, that's what the curly braces notation there tells me. So the first term of the sequence is a1, and that would be 1 over 1 squared plus 1, which is 1/2. The second term of the sequence, a2, would be 2 over 2 squared plus 1, which is 2/5. A3 would be 3 over 3 squared plus 1, which is 3/10. A4 would be 4 over 4 squared plus 1, which is 4/17. And A5, this is 1, 2, 3, 4, 5, 5 terms, is 5 over 5 squared plus 1, which is 5/26. So those are the first 5 terms. Right? Sweet and simple. You can graph a sequence. We're going to talk about the graphs. I guess before I show you graphs, we do before or after. Yeah, let's go ahead and do it. Oh, these are kind of nasty numbers. Yeah, no. We'll hold off for a second. We'll hold off on the graphs. All right, so these are our first 5 terms. Nothing fancy. Sequences can be defined in this way, right? Where I give you all of that information. I tell you the formula for an, and I tell you where n starts, like we did here, like we did in the other examples. Or I can give you just the list, and you have to infer from that list the formula. That can be a little bit tricky, like what comes next type problems. There is another way to define sequences that's maybe a little bit neater, a little bit harder to wrap your head all the way around. So sequences can also be defined. The term is recursively, where we have a formula, or I should say, where we are given the first few terms, then a formula, not for the nth term in general, but to calculate the next term as a combination of the previous terms. The formula that tells you how to get the next term from the last term or the last few terms is called a recurrence relation, right? That's a recursive recurrence. And those first few terms are often called initial conditions. There's a very famous example of one of these. I'm going to suggestively call the sequence Fn. Well, Fn is a sequence defined, and actually I guess I should do it like this. Fn n equals 0 to infinity is a sequence defined recursively by saying F0 is 0, F1 is 1, and Fn plus 2 is equal to Fn plus 1 plus Fn. So this thing here is called the recurrence relation. That's the formula that tells you how to get the next term from the previous terms. And these are called initial conditions or something like that. Initial values. Conditions. Turns out these sort of sequences, recursive sequences, are intimately connected to differential equations in a very cool way. But since you guys haven't studied differential equations yet, I don't get to talk about that today, which is sad. But we'll survive. What this recurrence relation says is that if you want to get the next term, you add up the term right before it and the term right before that. So like to get F5, you'd be plugging in n equals 3. You take F4 plus F3. And you can't really get started with that recurrence relation unless you know the first two terms, because this is what's called an order 2 recurrence. Let's find the first few terms of this sequence. We'll do the same thing. How about the first 5 terms? Well, I was told that F0, solutions in purple is nice. I was told that F0 is 0, and I was told that F1 is 1. Those are my initial values. How would I find F2? Well, if you come up here and you plug in n equals 0, you'll get F2 equals F1 plus F0. And those are two things that I know. F1 is 1, F0 is 0. So this is 1 plus 0, which is 1. So F2 is 1. So far, not a very exciting sequence. How would I find F3?
F2 plus F1.
Yeah, very good. It'll be F2 plus F1. And F2 we plug in, F2 we know is 1, F1 we know is 1, so this is 1 plus 1, which is 2. To find F4, I would add F3 to F2. F3 is 2, F2 is 1, so this is 2 plus 1, which is 3. Let me go a little further, because we already have here the first 5 terms, but I think it'd be fun to do just one more maybe. F5, by the recurrence relation, would be F4 plus F3, which is 3 plus 2, which is 5. So the sequence is 0, 1, 1, 2, 3, 5. The next term would be 8 and then 13. Does anybody know the name of this sequence?
The Fibonacci sequence.
Very good. Zero, 1, 2, 3, 5, 8, 13, 21, and so on, is called the Fibonacci sequence. And it has some neat connections to geometry and things in nature. Really, all of that is a consequence of the relationship between recursive sequences and differential equations. And if you're into that sort of stuff, there's a bunch of really bad books and YouTube videos talking about sacred geometry and the Fibonacci sequence, blah, blah, blah. It's mostly bullshit. But these are cool sequences. Recursive sequences are neat. There's another really important recursive sequence whose name starts with F that I want to share with you before we move on. And then we're going to talk about graphs of sequences and convergence. All right. Conditions, Kylie. Yeah. So you call them initial values or initial conditions, either one. So I'll use a lowercase fn here. And again, this sequence will start at 0. And this time what I'm going to say is f sub n plus 1 is equal to n plus 1 times fn. F sub 0 is 1. So I want to be clear about the language here also, right? Because this is a useful thing. When I call this guy F1 or F2 or F3 or F5 or Fn or Fn plus 1, we don't say to the. Something I've noticed a lot of people doing when they first meet these things is they call this F to the 5, or call this F to the n plus 1, or call this F to the n. Don't say to the. It makes it sound like a power, which it's very much not. The n, or the 4 or 5 or whatever, is an index. You can think of it as a variable. If you want to call it f of 4 or f of n, I'm fine with that because it really is a function. But please don't use the words to the. It's confusing, and people think it's a power when you say that, and that can be very misleading. All right, next example. So we're going to define the sequence fn by the rule fn plus 1. Yes, absolutely. You can definitely call it f sub 1. Yeah, I think that's what a lot of folks would prefer, or just f1, f2. But if you want to say the sub, that's fine also, because that's what it is, right? It's a subscript. by the rule, fn plus 1 or f sub n plus 1 is equal to n plus 1 times fn. And the initial condition or initial value that f0 or f sub 0 is 1. Let's do a few things. Let's find the first 5 terms and a formula for the nth term. I'll tell you right now, in general, given a recursive sequence, it's quite hard to find a formula for the nth term. Sometimes it's easy, but in general, to say like there is no method that always works that is available to you at this level. For example, finding a formula for the nth Fibonacci number, right? Finding a formula that spits out these numbers, a closed algebraic formula, is somewhat challenging. The standard approach uses power series and generating functions, and it's not pretty. It does involve that thing, the golden ratio. That's why people get so hot for the Fibonacci sequence. But in general, this is quite a tricky thing. Now, this particular sequence that I'm looking at here, he's not so bad. So once we write down the first few terms, I think you'll be able to see what that formula is going to be. Alrighty, here we go. F0 is 1, we know that. Solutions in purple. F1. I would come here and plug in n equals 0 to get F1 on the left, right? F sub 0 plus 1 is F1. That should be equal to 0 plus 1 times F1. So F1 is 0 plus 1 times F1. Oh, sorry, F0. F0. Plugging in n equals 0 here. 0 plus 1 is 1. So this is 1 times F1, which is also 1. 1 times 1 on a good day is 1. F2, to get F2, I would come back here and plug in n equals 1. So that's going to be 1 plus 1 times F1, which is 2 times 1, which is 2. F3, we just continue the same pattern here. I'm plugging in n equals 2 to my recurrence. So that would be 2 plus 1 times F2, which is 3 times 2, or 6. Let's do a few more. F4 would be 3 plus 1 times F3, which is 4 times 6, right? Is that right? Yeah, F3 is 6, 4 times 6, which is 24. And I'll do one more. F5 would be 4 plus 1 times F4, which is 5 times 24, which is 120. Does anybody know the name of this sequence? The sequence that goes 1, 1, 2, 6, 24, 120. The next is 720. Oh, that's okay. This one's less well known for sure. But for us, it's going to be way more important than the Fibonacci sequence. Here's a trick. So 2 is 2 times 1, right? 6 is 3 times 2 times 1. 24 is 4 times 3 times 2 times 1. 120 is 5 times 4 times 3 times 2 times 1. So what's the pattern here? it looks like in general,
N factorial.
yes, f sub n would be n times n minus 1 times n minus 2. And you just go all the way down until you get to 3 times 2 times 1, which is normally written as n exclamation point, called n factorial. The exclamation point means factorial. And factorials just say multiply all the positive integers less than or equal to the thing being factorialed. So like 10 factorial would be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay, this is a very important sequence for us. We are going to use the shit out of this thing, like all the time, all the time. It's a very quickly growing sequence, right? You notice that it starts off 1 and 1 pretty slow, but then 2, 6, 24, 1, 27, 20. After that, you're into 5-digit numbers. This thing grows very, very quickly. Just to practice a teensy bit with the notation. More practice with factorials. Zero factorial was f sub 0. That was 1. Some people don't like this, but it's true. And there are combinatorial reasons why this should be true and algebra reasons why this should be true. I invite you to investigate that on your own. 1 factorial is also 1, right? F0 is 1, F1 is 1. 2 factorial is 2 times 1. 3 factorial is 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. 5 factorial is 5 times 4 times 3 times 2 times 1. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. And these get really big, right? This is 120, this is 720. And beyond that, I don't have them memorized. They're just enormous. But if we wanted to, we could compute like 9 factorial. It's 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, and so on. All right. So these factorials, you just multiply all the positive integers less than or equal to that number. That rule works great, except when n is 0, and you just have to remember that 0 factorial is by definition the number 1. Turns out n factorial is the number of ways to arrange n plus 1 people in a circle, right? Where, you know, if you rotate the circle, everybody keeps the same partners, you don't count that separately. And since there's only one way to arrange one person in a circle, 0 factorial is 1. That's the combinatorial interpretation. The recurrence relation
You're muted, Professor.
Thank you. Sorry about that. We can thanks Cox Cable for being so awesome. So I don't know where you guys lost me in this, right? We did these computations, just writing them down with the definition. 9 factorial would be 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, right? And if you want to take the factorial of any number, you just multiply that number with all the positive integers less than or equal to that number. The recurrence relation that we wrote down earlier can be written in the exclamation mark notation. n plus 1 factorial, the factorial of n plus 1 is n plus 1 times the factorial of n. And you want to be very careful with the algebra of factorials. Don't assume that like you can distribute the exclamation mark, right? This is not n factorial plus 1 factorial. This is not multiplication. But this is another nice way to think of the definition of the factorial. Right, so like 9 factorial is 9 times all of this, which is 8 factorial. 25 factorial would be 25 times 24 factorial, which is 24 times 23 times 22, blah, 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 all the way down to 1. Okay, so in general, we can write the factorial recurrence relation like this, and sometimes this is a useful tool. Fun things to play with. What is, let's say, 2n factorial divided by 2n plus 1 factorial? Or is 2n factorial the same as 2 times n factorial? What other silly shit like this can we talk about? So just different things for you to poke your brain with. What else is fun? Ratios of factorials are important. Ooh. Is n squared factorial the same as n factorial squared? Stuff like this. The first one, you can simplify this just by writing everything out. You got to figure out what 2n factorial is. And that's going to require some care. But remember, it's the product of 2n with all the positive integers less than 2n. And the same you could do for 2n plus 1 factorial. This guy simplifies really nicely. The answer to both of these is no, but you should figure out why. You should play with these. Playing with factorials will get more and more important as we move deeper and deeper into chapter 11. But that's not what we're here for today. Today we are here to learn about sequences in general. So our next move, let's talk about graphs of sequences. It's just a collection of dots. Let's graph the sequence an equals 2n from the start, where n starts at 0, then 1, then 2, and so on. The way this works, instead of having y equals f of x, you have y equals an. And instead of an x-axis, you have an n-axis. So this would be y equals an. 0, there's 1, there's 2, there's 3, there's 4, there's 5, and so on. I'll call this up here 10. 8, 6, 4, 2, something like that. I messed up the scales a little bit, but you get the idea. A0 is 0. A1 is 2. A2 is 4. A3 is 6. A4 is 8. And A5 is 10. So this would be a graph of that sequence. In other words, the graph of a sequence is just a collection of dots. Points are of the form n, comma, an. All right, this is how it's done. And if I hadn't fucked up the scales here, you would see that these all live along a line. They all live along the same line as like y equals 2x. But the graph is just these dots because the domain is just these whole numbers. Let's look at another example. Let's graph the sequence. I'll give it to us in the other notation this time, 1 over n. And here n will start at 1. Well, the first few terms here are 1, and then 1/2, and then 1/3, and then 1/4. My parent call this 1. And on my horizontal axis, n-axis, I'll space things out. This. Okay. So A1 is 1 over 1, which is 1. Maybe I'll list these over here. A2 is 1/2. A3 is 1/3. A4 is 1/4, and A5 is 1/5. So, okay, A2 is 1/2. That should be halfway between 0 and 1. So there's the point 2 comma A2, 2 comma 1/2. A3 is 1/3. 1/3 is somewhere right around here. So there's the point 3 comma 1/3. A4 is 1/4, is exactly halfway between 0 and 1/2. I don't have the space to label it there, but somewhere around there. A5 is 1/5, is a little smaller, like this. The next term of the sequence would be 6 comma 1/6, which would look out like this, and so on. So this is the graph of the sequence 1 over n. If you look at the first graph, here these dots are just getting higher and higher and higher, right? It's just climbing more and more. So we would call this first sequence an increasing sequence, right? Because the terms of the sequence get bigger and bigger. This guy we would call a decreasing sequence because the terms of the sequence get smaller and smaller. Perhaps more importantly, the terms of the second sequence are all getting closer and closer to something as we go further and further out. In other words, the second graph has a horizontal asymptote. I can show you few more examples like that, and then we're going to define what it means for a sequence to converge. Are there any questions on how you get the graph of a sequence? Okay. So moving over here, let's look at one more guy. How about n over n plus 1? Or actually, no, better still. Just switching back and forth with notation. Let me go ahead and call this sequence Bn, just for fun. And let's define it to be -1 to the n plus 1 over n, where n starts at 1. To do this, we want the first few terms, and since this one's not super duper obvious, let's take a second and write them out. There is no b0, right? And here starts at 1. So b1 is -1 to the 1 plus 1, all divided by 1. 1 plus 1, the power there is 2. This is -1 squared over 1, which is 1 over 1. So b1 is 1. b2 is -1 to the 2 plus 1 over 2, which is -1 cubed over 2, which is -1 over, -1 over 2, -1/2. b3 would be -1 to the 3 plus 1 over 3, which is -1 to the 4 over 3. -1 to the 4 is +1, so this is +1/3. I'll put a few more terms over here. b4 is -1 to the 4 plus 1 over 4, which is -1 to the 5 over 4. -1 to the 5 is -1, so this is -1/4. And b5 will stop here. This is -1 to the 5 plus 1 over 5, which is -1 to the 6 over 5, which is +1/5. I guess I've got room for b6 here. Let's do it. b6 would be -1 to the 6 plus 1 over 6, which is -1 to the 7 over 6, which is -1/6. All right, here's the first 6 terms of this sequence. And what you notice is that some of them are positive and some of them are negative. In fact, every other term, you flip sign. Goes positive, negative, positive, negative, positive, negative. That's coming from the power of -1, right? Powers of -1, -1 to the n, -1 to the n plus 1, whatever. They alternate between being positive and being negative. And if I wanted to graph this sequence, I need to allow for both positive and negative y values. I'll mark this up here as +1, this down here as -1. And then I'll chop up my horizontal axis 1, 2, 3, 4, 5, 6. B1 was +1. So here's that first point on the graph. B2 was -1/2. So that's like right here. B3 is +1/3. That's like right here. B4 is -1/4, which is like right here. B5 is positive 1/5. Again, pretty small now. And B6 is negative 1/6. It doesn't have a hard time fitting them in here next to that label, but here's B6. Now there is no nice curve that these all sit on, like maybe some sort of weird decaying sinusoid or something, but this would be our graph. And this is your n-axis, and this is the graph y equals bn. The next term would be like right here. And then the next term after that would be like right here. And I'll ask you, what do you notice about these dots as we go further and further and further to the right?
Getting closer to the x-axis.
Yeah, exactly. To the, I'll call it the n-axis. Or you just call it the line y equals 0. So as we go further and further to the right, the dots get closer and closer to the horizontal or n-axis, which is the line y equals 0. Yeah, this is some kind of oscillation. That would be an accurate statement here. The -1 power causes the sequence to oscillate back and forth between positive and negative. This is kind of like a sequence version of a damped harmonic oscillator. Not quite, but close. It does the same sort of thing, right? Where have you heard this language? As we go further and further to the right, things get closer and closer to 0. What does that remind you of? Specifically, the further and further, closer and closer language. What does that sound like?
Asymptotes?
Yeah, asymptotes. Richard's got the word I'm looking for there. It sounds like a limit, right? Closer and closer, further and further. Sounds like a limit. The calculus operation, so pause again real quick. The graph of a sequence is just some dots. So there's no way I can talk about a tangent line, right? There's no hope of a concept of a derivative here or a tangent line here, because those require like smooth connected curves, right? In order to differentiate, a function has to be differentiable, which means at the very least, it has to be continuous. And in fact, there's more to it, right? Remember that from Calc 1. This thing, definitely not continuous in any sense. Yeah, the graph is just a bunch of discrete dots. These bitches are not connected to one another. And it cannot possibly be smooth because it's not continuous. So there's no hope of derivatives. Also, even though we draw these dots as having like some actual width, because my pen isn't infinitely narrow, we know that a point, which this is supposed to be a single point, doesn't have any width to it. So there's no area underneath this. I can't talk about the area underneath this infinitely narrow point. So the normal calculus operations, derivatives, tangent lines, or integrals and areas really don't make sense here. There's one calculus operation that makes sense, and it's the one that's alluded to by this language, and that's a limit. Not a limit as n goes to 3, because again, I can't get closer and closer to this point from anywhere nearby on the graph. It just fucking jumps right to here. But I can talk about what this thing does as we go further and further and further to the right. That's a limit at infinity. So the calculus operation, the only calculus operation which makes sense for these, are limits as the independent variable here, which is n, goes to infinity. And this is where we're going to meet our second notion of convergence. First, let me, I guess, define the thing. So we say that lim n to infinity of some sequence an is equal to the number L if the terms of the sequence an can be made as close as we want to L by taking n sufficiently large right? So if the terms of the sequence an get closer and closer and closer and closer to that number L as n gets bigger and bigger and bigger and bigger, then we say the limit of the ans is L. The limit as n goes to infinity of the ans is L. In the example we have right here, the terms of the sequence 1, -1/2, +1/3, -1/4, +1/5, -1/6, +1/7, -1/8. These can be made as close as we want to 0 by taking n really, really, really big. So, for example, for the sequence Bn above, L is equal to 0. That is, the limit as n goes to infinity of -1 to the n plus 1 divided by n is equal to 0. I will give you some nice tools to kind of show this, but I want to point out that the sort of normal sequence or normal limit operations might not always work here. It's true that the bottom is going to infinity because the bottom is just n, but the top, the limit as n goes to infinity of -1 to the n plus 1, this does not exist on its own. You can get here with the squeeze theorem, and you can get here with a special theorem for sequences that I'll share with you in a little bit. But here we're just getting it from the graph. Right, looking at that graph, as n gets bigger and bigger and bigger, these dots get closer and closer and closer to the line y equals 0. So that limit is 0. This is the main operation we use with sequences, limits at infinity. That's the only one that really makes sense. Questions on the definition? Or why that purple sequence Bn above goes to 0? Okay. The bottom sequence down here, 1 over n. The limit of this guy would also be 0. These guys are getting closer and closer and closer to 0 as we go further to the left. I'm going to define for you now what it means for a sequence to converge. This is your second notion of convergence, right? You have a notion of convergence for improper integrals. We say that the sequence an, and when I leave off the n equals 0 to infinity or whatever, I'm just saying it could start at 0, it could start at 1, could start wherever. We say that the sequence an converges if the limit as n goes to infinity of an, two things. We need it to exist and be finite. That's what it means to say that a sequence converges. And if that limit from n to infinity and does not exist, or is not finite, then we say the sequence an diverges. Right, so again, it's like an infinite process leading to a finite result. If the infinite process, this list of things, gets closer and closer and closer to some particular number, finite number, then we say that that is a convergent sequence, or that that sequence converges. Let me show you a couple other examples and kind of try to recharge your brain with the tools from Calc 1 that many of us have probably forgotten. Classify the sequences as convergent or divergent. If the sequence converges, state the limit. And I'll give us some sequences to play with here. How about an equals n plus 2 over n plus 5. How about bn equals 2 to the negative n. Cn equals the inverse tangent of 5n, and dn equals the sine of 1 over n. Each of these can be handled using the shit you know from Calc 1. But you got to remember your Calc 1. For any sequence, the thing to do is look at the limit. So we're going to take the limit as n goes to infinity in each of these and see what we get. The limit as n goes to infinity of an is, and please, 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 this is Calc 2 now. You need to use good notation. Don't leave off your limits. Use good notation. It's so important, especially as we move into series after this. You need to be good with your notation. So write the limits, write the symbols, don't omit shit. This is limit n to infinity of n plus 2 over n plus 5. And the idea is you can treat the n's the same way you treat x's. Right? You can treat the n's the same way you treat x's. So if this was limit x to infinity, x plus 2 over x plus 5, what would you do then? It's the same as it was in Calc 1. What do we do here?
Plug in.
Well, if I plug in infinity, so yeah, fair enough. If I plug in infinity up here, I get infinity plus 2. And if I plug in infinity down here, I get infinity plus 5. which is indeed an indeterminate form. It's an indeterminate ratio. So we could say, okay, this is like infinity plus 2 over infinity plus 5. And adding 2 or 5 to infinity isn't going to change it. That's still infinity, and the bottom is still infinity. So how do we handle this? Yeah, we could use L'Hopital's rule. In fact, let me make a small change here. Let me make this 3n plus 2 over 2n plus 5. I apologize for doing this. I know that that's frustrating, but so this would be 3 times infinity plus 2 over 2 times infinity plus 5. It's still infinity over infinity. I'm just doing this to help bring out some features of these sequences. We could use L'Hopital's rule. This is an indeterminate ratio. So L'Hopital's rule applies. L'Hopital's rule would say take the derivative of the top and the derivative of the bottom. Well, I said we can't differentiate sequences, but I also said you can treat these the same as you treat x's. It's true that you can't really differentiate a sequence, but you can still use L'Hopital's rule. The rules really do work the same. The idea is that 3x plus 2 over 2x plus 5, the dots here are glued to that graph. So they have to follow that graph. So you can kind of, again, pretend like this is a continuous function or a differentiable function. If we take the derivative of the top, that's 3 plus 0. You take the derivative of the bottom, that's 2 plus 0, right? The derivative of 3n, just like the derivative of 3x, would be 3. The derivative of 2 would be 0. The derivative of 2n, just like the derivative of 2x, would be 2, and the derivative of 5 is 0. So this would just be 3 halves. And that's correct. But here we actually didn't need L'Hopital's rule. If you don't want to use L'Hopital's rule, we could divide top and bottom by n. And there we would see lim n to infinity 3n plus 2 times 1 over n divided by 2n plus 5 times 1 over n. Distributing our 1 over n's, we would get lim n to infinity 3 plus 2 times 1 over n over 2 plus 5 times 1 over n. And then the 1 over n's go to 0 as n goes to infinity. This is 3 plus 2 times 1 over infinity divided by 2 plus 5 times 1 over infinity. And 1 over infinity is 0. So this is 3 plus 2 times 0 over 2 plus 5 times 0, which is again 3 halves. This second way of approaching the problem, where you divide top and bottom by whatever the largest power of your variable is, by whatever the fastest growing term is, I call renormalization. And it's a very useful trick. It gets you around using L'Hopital's rule. Let's look at the others. Oh, sorry. So what's true about the sequence AN? We want to classify as convergent or divergent. Is the sequence AN convergent or divergent? Anybody? Convergent, yeah, very good. It's a convergent sequence because the limit exists and is finite, right? The limit was 3/2. All right. So this first sequence here, AN, this is a convergent sequence. We would say that this sequence converges to 3/2. All right, next up. Lim n to infinity Bn. That is the limit as n goes to infinity of 2 to the negative n. You could just go ahead and plug in infinity here, but I would advise rewriting this first as lim n to infinity. 2 to the negative n is the same as 1 divided by 2 to the n. And as n gets bigger and bigger and bigger, what does 2 to the n do? What is 2 to the infinity?
Converges to 0.
It's true that the whole sequence here will converge to 0. Yeah, because 2 to the infinity is infinity. You raise 2 to a very large power, you get a very, very big number, and 1 over infinity is 0. So the sequence Bn converges to 0. Okay, moving on. Lim n to infinity of the next sequence, which we call Cn. That would be the limit as n goes to infinity of the inverse tangent of 5n. Here you need to think a little bit. What does the inside do as n goes to infinity? What does 5n do as n goes to infinity?
Also goes to infinity.
5n goes to infinity, yeah. And what does the inverse tangent function do as its inside goes to infinity?
Does it go to 1?
Not 1.
Pi.
Let's look at
Pi
the
over
graph.
2.
So here's the graph of arctan. All right, so the graph here.
It's pi over 2 and negative pi over 2.
So this is the graph y equals arctan of x. And my sequence here, 0, I'll call this 5, 10, 15, 20. My sequence here is dots along this graph. So yeah, those purple dots, they have no choice. Here's the n equals 0 dot. The purple dots have no choice but to get closer and closer and closer to whatever that horizontal asymptote is. And that horizontal asymptote is pi over 2. So this sequence I would say the sequence Cn converges to pi over 2. And these are all just limit tricks that you should remember from Calc 1. I'm just trying to help jog your memory. Lastly, the sequence Dn that's the limit as n goes to infinity of the sine of 1 over n. And just like the last problem, the trick to this is to think about what's going on inside. What does 1 over n do as n goes to infinity? I'm really
That
asking.
would be 0, so sine of 0.
Very good. So 1 over n goes to 0 as n goes to infinity. So this is going to the sine of 0. And what's the sine of 0?
0.
0. Very good. So the sequence Dn converges to 0. Okay. Now there are a handful of theorems, right? This is the basic gist. You've got your renormalization trick. You've got L'Hopital's rule. And then you've got all the limit stuff that you know from Calc 1. Really, those are all things that you should know from Calc 1. But these are the main basic tools for taking limits of sequences. There are some other tools. So one of these theorems we've been using, actually several of these theorems we've been using. If an is equal to f of n, where f of x is a continuous function, then the limit as n goes to infinity of an is the same as the limit as n goes to infinity of, or sorry, x goes to infinity of f of x. So this says you can do the stuff from Calc 1. This says you can treat the n's like x's. That's all. That's all this is. Treat n's like x's. You can use all the stuff from Calc 1. We've been using this. We've been using this implicitly. There's nothing magic here. This next theorem says if f of x is continuous, then the limit as n goes to infinity of f of an is equal to f of the limit as n goes to infinity of an. In other words, like sine of 1 over n. Sine is continuous. So you can just take the limit of the inside thing. That's all. So you can take the limit if you've got a composite function, if you've got a sequence that's made up by shoving a sequence into some continuous function, then you can take the limit of the inside and just f of that will be your limit. These two we've used implicitly already. There's nothing magic going on here. It's just what your mind thinks is true. It's true. This next one is new. If the limit as n goes to infinity of the absolute value of an is 0, then the limit as n goes to infinity of an itself is 0 as well. This is kind of a partial converse to the previous theorem. Let me make sure I'm not missing anything here. I know there's other theorems that I want to share. I think we're about out of time, actually. So let me take a quick look here, see if there's anything I'm forgetting. Oh, no. So notation, that's good shit. Definition of a limit, definition of convergent. Yeah, the squeeze theorem. Squeeze theorem is implied by the other ones. So you do have to remember your squeeze theorem. L'Hopital's rule works. That's our continuous function thing. Okay. Yeah, so we still need to talk about special sequences, geometric sequences in particular. We will do that next time. Let me just show you. No, I don't think I have time, do I? No, I gotta go. All right, so this is where I'm gonna leave you guys for today. You're gonna have a new homework opening up today that has a bunch of sequence problems in it. Please work on that as soon as you can. The more you practice with this, the easier the next few sections will be. Remember, this is the hard part of the course. You really do need to be digging in now. So please, please, please work hard on this new homework. Take it quite seriously and you will be okay. If you're not done with the improper integrals homework, you can submit an extension request. I'll clear those out this afternoon as soon as I can. But yeah, that's it. All righty. I'll see you guys next time. I am working on your tests. I'll have them for you as soon as I possibly can. They're not ready yet, but I'll have them for you very, very soon. So yeah, that's it. If you need to see me in office hours, I got one of those from 1 to 2 p.m. Otherwise, I'll see you guys next time.